last time, we went through section 8.1, 8.2, and I think, did we end with 8.3 on this? Does this seem familiar to anyone about comparing DynaQ and DynaQ plus? Because I do think we went over this already. All right, we can go back over it if there's questions about it. And or the exercises. I don't know. I'm just asking. I don't know if anyone who was here remembers finishing this section.
The descriptions about DynaQ were made sense with the two experiments of the blocking structure, and then the better path one where the difference between DynaQ and DynaQ plus with the extra parameter of having a weighting towards states that were not visited for a while helped out with the exploration part for the blockchain maze and the better path maze.
Mm-hmm. Okay. Well, yeah. So in the blocking maze, we sort of, have a certain environment, and then the optimal path gets changed. Like the path that's optimal is cut off. And if you apply DynaQ to this, there's this plateau time where it takes time for the model to learn that it's incorrect. And, eventually it should learn the new path, although in this case, the path be longer than the path in the original case. So this plot would show the accumulated reward over time, and when it sort of approaches a straight line, that's when it essentially knows the optimal policy. So the DynaQ can actually correct itself in this case because it will attempt to follow the optimal policy and collect data, and that data will update the model because it's wrong. In the case of the shortcut maze, though, this was a problem where there is a longer path to the goal at the beginning, and then a shorter path is opened up. And the idea is once we learn the optimal path to the goal and the model is basically accurate for these states along the optimal path, then if this is switched out after 3,000 steps, so here, like, there's a shortcut's opened up, but the model doesn't get updated. And the agent will continue to follow the same trajectory as before. And the model is actually correct along this trajectory still, because this path is still, like if you're in this state and you take this path to the goal, that would still have the correct value estimate. These states over here will be wrong, but if the model or if the agent never actually visits these states, then it will never sort of notice that there's a problem. So this is like a pretty bad failure case in the case of a change to the environment where DynaQ really will never, I mean, even with the exploration parameter, the way it's set up, it will never really, find this correction to the model. And, there's a comment in the book about how the visit time, like, even though there's an exploration parameter, so it could like visit, some of these states, but in order to really correct the model, it has to like repeatedly take these exploration steps. And that's why there's this other approach introduced called it's actually not, I guess they don't have pseudocode written out anywhere in the book, but the idea is that in the part of DynaQ in the planning phase, when this update happens, you sample this reward, and in DynaQ Plus, which it should show it here, wherever the so there's this bonus added during the planning step. So remember, like the planning is where the model is used to make queue updates without actually sampling from the environment. So the idea is that for states that haven't been visited in a long time, we have to keep track of the last time states were visited for this method. Then it will basically add a bonus to the reward for that. And then that will end up increasing Q values, not just to actions that haven't been visited in a while, but because we continue to loop and update the Q function for all of these visited things, it will actually end up back propagating and updating, increasing the values for any sort of action that in the future leads to a visit to one of these states that haven't been visited in a long time. So this will end up correcting the model. Now, I don't know if things actually have never been visited. I mean, there is an issue here if the model doesn't even have any information for certain state action pairs, but I think there might be some other mechanism of dealing with that in here. Well, I mean, the policy, yeah, I mean, that part will sort of be handled by the epsilon greedy policy being followed by the environment sampling in the first place, but, it will at least make sure that, the model doesn't convince itself that some value is correct forever. This will also guarantee that any previously visited state, will eventually be reached, even if it's many, many steps away from what seems to be the optimal trajectory, because, those faraway states are going to keep their reward bonus is going to keep getting propagated back. So we can see here that this is actually for the blocking maze where DynaQ is also able to learn it, but DynaQ plus learns it faster. That this plateau doesn't last as long. And then in the case of the shortcut maze, which this is this plot here where in the case of DynaQ, the shortcut maze, the optimal policy never changes. But for this, after a while of continuing to follow the previous optimal policy, it will eventually learn the new optimal policy. You can see here there's this starts separating where, there's this new higher value of the slope of this curve, which indicates it has successfully learned or found the shortcut that was opened up. So this also wouldn't be a problem if we weren't using a model at all, because this is really if we're just following the epsilon greedy policy that in the environment, that will also cause the same thing. But the issue with DynaQ is that like the whole point of it is that we're going to try to leverage the model to do a lot more Q updates. So you end up more quickly getting Q functions that don't, make it look like you should only go to places where the model shows it is promising. But we didn't have this problem before with just doing tabular like TD0 like Sarsa with epsilon greedy. Although I guess you could do that as an experiment and see how even something like Sarsa handles this blocking maze or shortcut maze. I'm not sure exactly what would happen in that case. Because I mean, yeah, you still have to do the Q updates, but in that case, we're just relying on epsilon greedy for exploration. Yeah, so those are sort of the two, like one of the main approaches to explaining how we can still take advantage of planning, even in a case where, the environment might change. There is this one exercise, which I think I have like a pretty good answer to. So, in the planning phase, with DynaQ Plus, what happens is we have in the planning phase, we're boosting the reward for, actions that haven't been seen recently. But in this exercise, they're saying, well, what if instead of that, we keep the Q updates the same here, right? But then when it comes to selecting actions, like when we update the policy here, instead of doing this like epsilon greedy thing with respect to Q, what if we just apply this bonus to the action selection? So, we take the argmax of Q and we will add a bonus to states that haven't been visited in a long time, right? So that would occur at this part, right, where we actually select a action to interact with the environment, right? Because like we have to, if the model is wrong, the only way we're going to correct it is by eventually sampling something from the environment that changes the model. Right. So we may have to, and the whole problem is like in the shortcut case, right? There's some shortcut that is opened up in a place that the previous optimal policy would never visit. Like it could be very far away. So there's like no incentive to go there or even consider it. But here we can add this bonus. So, with the hopes that we would explore, one of these suboptimal actions that hasn't been visited in a long time. So the question is, if you take this approach, like, is there any reason to do this instead of what is suggested in DynaQ Plus, which is to instead boost the reward in the planning phase? And you can, I mean, so there's a question of carrying out an experiment. So I'm trying to think I did some experiment here. What experiment did I do? So this would be showing, so I'm gonna, if I actually implement this approach, right, where, and let's see how, if you see how I implemented this DynaQ plus prime, let's say, where now we're doing the bonus part, but now it's different. So the planning now is the same as before. We're doing the normal Q update, right? These all look like the normal Q updates with a, constant step size. And then here, when it comes to the actual policy step, where we're gonna right? So this policy is used to take a step in the environment and get real data. So here I am taking the greedy policy with respect to not the Q function, but the Q function plus this bonus term, right? Where the bonus term is related to the length of time since a state was last visited. So here's some results. So this is showing the the blocking maze, right, where it has to learn um, the new path, and this would be the shortcut maze, where there is a new optimal that it has to learn. So the blue line here is DynaQ plus, one we already had, and we know that DynaQ plus is successful at both of these. And then, the DynaQ plus prime is this alternative approach where you apply the bonus to the policy action selection. The question is why, if anything, why is the normal DynaQ plus a better approach, since this seems like we're just directly incentivizing visiting states that haven't been visited in a while. Whereas, in the DynaQ plus approach, there's this indirect way of boosting those unvisited states in the planning phase, where we no longer have accurate rewards in that method because we're changing the reward values. Whereas, in this method, all we're doing is giving the exploration bonus just for the policy, but the Q values will not be affected. So here you can see, well, there is something kind of noticeable about this experiment, in particular with the shortcut maze, which I don't know if you can tell here how it doesn't seem to actually learn the shortcut, this approach. Right. Now it does work for this, although maybe a little slower, but that may not be a problem. Like I may have just chosen bad parameters for this, or the method could work. But this case seems to be particularly bad. So I think like it is worth thinking about, because like I might have thought, like, if I had this problem, this exploration problem with the model, I mean this approach actually seems pretty like reasonable, right? As opposed to the DynaQ plus. So I think it is worth thinking about why this maybe has problems, or there's cases where it doesn't work. Yeah, so I don't know, I can sort of go over what I think is the reason for that, but if anyone has any idea or thoughts about this, feel free to say something or bring it up. Or if there's any question about this whole, thing in the first place. I don't know if this whole thing is, these bonus values are confusing with the actual mechanism for how the agent learns learns new things in both of these cases.
Well, it seems like in both of those cases for DynaQ and DynaQ plus. Actually, never mind.
Okay, well, no one has. I mean, does it seem intuitive, like like this should work? For fixing the model, or finding the shortcut.
Well, theoretically, it should be able to help find the shortcut by basically introducing the entire by changing the entire optimization function to be a balance between between the optimal Q value, well, Q policy, and then the difference between visited states, which it would seem like it would eventually lead to a less better policy because of the other factor basically limiting
Yeah.
limiting
Or remember, so yeah,
utilization.
so this bonus factor is going to be applied to the policy where we actually sample something. But in the planning phase, we still have we're still relying on the model that we have. So, you have to imagine that, this agent has already interacted with this environment. Like, let's say for a while, it's, randomly moved around for a bunch of episodes. So it has a model where, this state is blocked off. So like this is a very bad state. In fact, this would be the worst state to be in because this would be the farthest away from the goal in this case. So you have this model and you keep, learning off this model, and the model, is telling you that these states are very bad. So we still have that now. So we have our Q function is sort of optimized to the model, and then when we are choosing to make steps, maybe we have this bonus factor. So maybe, obviously actions that take you to the right here are going to seem really bad, right? Like we never go to the right from this state because everything over here is bad. So, maybe this bonus after a long enough time where like haven't gone right in forever, right? So we will eventually maybe take a step to the right. Okay, I think that you could probably see how that would happen. So then we make a step to the right. And now, suddenly we're in this new state where we probably, haven't visited any of these actions in a long time, right? Because like if we haven't stepped to the right in forever, then that means we haven't stepped to the left in forever either from here or to the right, because stepping left from here is going to be just as new as stepping right from here. So even with this bonus, what I suspect will end up happening is, you'll maybe go to the right here after a while. And then the most likely thing is you'll just immediately go back here because this state value is estimated to be much higher than this state value, but it also hasn't been visited in a long time. And then maybe after not having visited right again forever, you do this. And then maybe after that second layer of visiting this new state, then maybe this state going to the right will have a high enough bonus. But you could see that, because we're only applying this here, this bonus doesn't end up propagating it all out from this point. Because remember, we are looking at state action pairs, not just states. So like every time we go further away from the optimum, the action that returns us back to the optimal path is just as, seldom visited as the action that takes us further away from the path.
So essentially, that difference between that policy of having the actual policy being added to try to optimize or trying to look at the trying to look at the visited states, it would still be a very low probability case, and so it would only propagate once or two, one tile, and then it would only slowly build up probability, but that is a very low likelihood chance and will probably take a lot of computation.
Mm-hmm. So if you note in this note on DynaQ plus, this encourages the agent to keep testing all accessible states and even find long sequences of actions in order to carry out such tests. I believe that the problem with this other method here is that this other method doesn't encourage at all long chains of actions to reach unvisited states. That's the problem. So, this shortcut, this isn't a very big problem, but you could imagine that if the problem was huge and it might take like 1,000 steps to even reach the part where we find anything out, it's just never going to happen. It's going to take so many extra steps. Whereas, the nice thing about the other bonus is that, those unvisited states, they just become like a ticking time bomb in the MDP. So like this thing, if we just never end up here, this is going to keep growing and growing and growing the bonus in the planning phase. And eventually, those bonus rewards are going to eventually encourage the agent to just take a path straight over to these unvisited states because, it's going to end up affecting all the states that can be reached as well, like all the states that reach this state. So that may come into play in some later examples as well. But I suspect that there's probably, if you wait long enough, this method may find the shortcut. But I mean, you can see it's not really working yet. And the whole point of this was to try to find the shortcut faster than DynaQ would. And this isn't really happening here. So yeah. Now, of course, you got to know, you notice this part, right? So like this finds the shortcut, but you can see that in order to find the shortcut, it had to take some bad, path first, right? It had to explore a little bit. So this little plateau here is like you have to sacrifice a little bit of exploration to find the shortcut. But then, you would expect that to happen, right? Like the performance has to degrade at some point in order for it to actually explore anything. So I think that's good for this section. Is that or any further questions about this or these two things? I don't think we don't really have to talk about this one.
Yeah, I don't have a question about the difference between the DynaQ Plus and the DynaQ Plus with the policy being changed compared to the visitation state being added into the model.
Mm-hmm. Okay, well, this next section talks about an alternative method. So for using the previously visited states. So in DynaQ, we keep track of this, history of visited states. And when it comes to planning, we just loop through the history, and sample from the history for some, number of times, like, some maximum number of steps, or in this case, it will always be the same number of steps. In this section, there is this alternative method called prioritized sweeping, where instead of this, we maintain this priority queue of the history of visited states. And the idea behind the priority queue is that based on the model, there are certain states that we would predict would have a change to their value estimate from whatever the current value is. Now, of course, we need to do some extra computation to evaluate this priority. Like if you see in this priority queue, when we loop n times, this is like the number of planning steps. For each planning step, we have to look at, all of the states that lead to the current state we're considering in order to update the priority queue. So we're sort of using the states and we're looking backwards, using the model as a guide to which states, so when this is like all these states and actions that are predicted to lead to S. The prediction is from the model of, you know, how many, in this case, we're considering just a deterministic environment. So the model will tell us exactly, you know, what state or set of states leads to this state. But, you know, here, there's sort of two parts where we update the priority queue. One is after we actually get real data from the environment. And, you know, this P represents the sort of the size of the queue update. Right? But in this case, like we don't actually update the queue function yet. So we have the size of the queue update and we put it, or sorry, I mean, we're going to use the size of the queue update to guide what the priority is. So the highest priority will be to the thing that would have the largest queue update. Right? And then all the queue updates happen in the planning phase. And the planning phase is always taking the state action pair with the highest priority. And then the priority queue is updated after every queue update. Okay. And then once the priority queue is empty, we're done. Or, you know, we do this n times, but this also has the possibility of terminating before n is reached because, you know, the queue could become empty before then. So, you know, the hope with this method is that we do much more efficient planning steps because we're going to concentrate our planning in places where the model itself would cause a change in the queue function. Because like the whole point of the planning steps is we use the data we already have to update the queue function, but we can also use the model itself to know where the queue function, you know, would actually become updated the most quickly. So, you know, this computation is worth it if it results in much more useful queue updates than we would do by just randomly sampling from states and actions that we've already visited. So this is showing the impact of this on a grid world example. So the idea is we have this grid world like here, this one, where, you know, we showed here that obviously if we add more planning steps, this can solve the problem in far fewer episodes. And then, but, you know, we also know, like, just from this very simple environment, what the optimal path is. So we can also just say, like, okay, however many, you know, we'll just keep track of whatever planning steps we pick, interactions with the environment of just how many of these updates we've done total, because, you know, in the end, we're just going to update the queue function some number of times. And we can then ask, okay, well, how many total, you know, updates are required before this finds the optimal path? And then you can sort of generate larger mazes than this, but keeping sort of the same structure where we have, you know, 3 different walls in the maze. And then from this experiment, we can see how much more efficient the prioritized sweeping updates are than the normal planning steps. So that is what's shown here. And this is like a log scale of the number of updates that are required. You can see there's some, you know, order of magnitude improvement here using the prioritized sweeps than the DynaQ agent. And I have got sort of, so this is just showing, in my case, sort of the example mazes, like how they scale up. So it's the same sort of structure, you just sort of the wall gets extended, and this looks kind of ugly because I'm cramming it in one line, but you know, you get the general idea of how the mazes look. And then, you know, this is showing, you know, scaling up the maze size. But for prioritized sweeping, so for the smallest maze, it takes only 54 updates to find the optimal solution, or sorry, it takes 180 updates to find the optimal solution. And, you know, DynaQ is taking like 15,000 steps and like 40,000, 48,000. I think I actually cut this off at some point too. So This probably doesn't look as extreme as it should. But yeah, you can see already here, like, you know, 400 updates compared to 48,000 updates. This is like quite significantly better. So even with this extra computation of computing the priority queue, it should still be really useful. Or yeah, just focus. I mean, I don't know if this would always be preferable over DynaQ. I mean, probably if you're doing, because this is just sort of a strict improvement on DynaQ. I think, yeah, they don't really address here cases where this wouldn't work that well, but it seems like it's just a better way of making use of the model. I guess maybe this fails badly if the model is wrong again, because again, this whole scheme doesn't take into account like DynaQ plus, but of course, maybe you could compute a priority queue using the exploration bonus, and that would fix it, but I'm not sure. I haven't done that experiment myself. But they show here, I guess, for this example, the state space is like very large. Like, so this becomes more and more important the larger the state space gets, as you can. I mean, the percentage like improvement of prioritized sweeping maybe is about the same, but the amount of updates that you're saving get a lot more valuable the larger the state space is, because you know each one of there's just a significantly more state action pairs that you are avoiding dealing with just in total time. So yeah, I mean, the percentage saving becomes more and more important the longer each total update takes. So I think it's very easy to come up with examples where the state action space gets very large to the point where you really would want to have these more efficient planning steps. So yeah, are there any questions about this? How this works compared to the just regular DynaQ? I mean, you can look at the code. It's probably, using the priority queue, understanding it, probably be easier if you actually like implement it yourself. But the general idea isn't that hard to understand. We're just trying to predict from the model, which queue updates are going to be the most significant. Okay. Well, we can move on. I mean, this section just sort of explains some concepts from before, but puts them sort of in one place. So if we consider the distinction between expected updates and sample updates, where we sort of started with these dynamic programming methods in chapter 4, where we know all these probabilities. So for these methods, we just explicitly calculate these values using the probabilities, or in the case of optimizing, we can directly evaluate the maximum, knowing all these future probabilities of transitions. What they show here is what this wasn't really covered in chapter 4, but like the value iteration algorithm that was shown before could also be done with Q values as well as values. I mean, the reason why we used the state values instead of the state action values is because normally we need the state action values when we don't have access to the probabilities. When we have access to the probabilities, we can always recover the Q from the V. and vice versa. So, you know, using V ends up saving space because we don't actually have to save, information about all the state action pairs. We can just have the state values and then we can compute this stuff using the probability function. But then in contrast to these expected updates, we had the case where we use sample updates like in SARSA, where, we just estimated this, the value of the state action pair by, partially bootstrapping on the future value, but by sampling from the transition. And, if we actually know the policy and the probability transition function, we don't have to sample, we can just compute it with probabilities. But there are cases where maybe the sampling is a good idea, even if we have all of the probabilities. And it really comes down to how much branching there is in the environment. So by the way, just as a summary, this is showing the expected update, which, this sort of update would be used in Q value iteration. I think anyway, should be this. So actually Q, yeah. So this equation corresponds to this Q value iteration where now, I mean, it's actually a little more cumbersome than the V one because we have to not only consider, the transition from the state action pair, but also all of the actions that follow the transition states. So it's a little bit more, nesting, but this is still, this is all entirely possible with access to this. And, in contrast, we have the Q learning type update, which makes use of sampling. I mean, this maximization step still occurs down here, but here, instead of considering all the transition states, we're just sampling a single step in the environment. And, both of these will end up converging to the same thing. In this case, we are explicitly summing over all of the transitions with their corresponding probabilities. In this case, we are just observing a single one. So if you were to do so many sample updates that you actually just covered all of these state action pairs, then it would make sense to just, do the expected update. But if we don't have enough time to compute the whole expected update, then, this doesn't really give us any useful answer unless we just complete the entire sum. But the nice thing about the sampling is that each sample is an unbiased estimate of this value. So even if we can only take a few samples, like we're still incrementally improving the solution. We don't have to do all of them. So they set up this kind of experiment here where they make some assumptions about, what the error starts with and that all of the values at these transition states are correct. So the idea is like all these other, like the bootstrap Q values are all correct, but the current value is not necessarily correct. And we want to update it. And we could either update it by doing all of this entire sum, or we could collect a certain number of samples. And here, this is showing how once we evaluate a number of samples that equal, like here, the branching factor is just the number of these things we have to consider, right? How many like branches are there from the state action pair? So if we do an update for each of the branches, we can just do the expected update, and that will completely update the Q value to be no error in this case. And, for that number of updates, the sample updates are less efficient, especially when the branching is low, because, we have this learning rate and we might not, optimally, like we might not, that there's this sampling error that we have to consider. So everything over here, you just want to do the expected update. But if we only have time to do a certain number of computations, like on this part of the graph, and there's this enormous amount of branching. So here, like if we have a branching factor of like 10,000, we could collect like 1,000 samples. And we're going to do like 1,000 Q updates. And that, in this case, will actually already reduce the error quite a bit, even though we haven't had nearly enough time to sample all of the transitions. And, so this gets more impressive the more branching there is. And this is also a case where they've assumed some, degree of branching where there's a certain number of transition states visited, and they're all equally likely to be visited, and each one of them will, provide the bootstrap value at each of those transition states will provide an inaccurate update. Like those values have already converged. So if you have a problem with very large branching, even if you could, calculate all the expected updates, it depends on the time constraints. Like if you don't have enough time to perform all these updates, then you may just not be able to do the expected updates at all, in which case you're forced to do this. But the good news is that the larger the branching factor, the more quickly we get to very low error with far fewer samples than we would actually need to do the full expected update. And there's this question here, which is how in this analysis all the branching states were equally likely, but in most problems there's a skewed distribution where some of the states are much more likely to transition into that than others. The question is, would this strengthen or weaken the case here that the sample updates are more efficient than the expected update for when we have limited computational resources? So does anyone have an idea about this, whether if this scenario is like sort of a worst case scenario, or if the distribution is skewed, would it improve or worsen this type of graph if we were to make it with a skewed distribution?
Well, based on the result of looking at what happens when it's very skewed, it seems like it's reducing the amount of Q computations that is needed.
Oh, and what? Wait, say that again. When what is skewed?
Well, uh, looking at figure 8.7, or is that just the? Never mind. No,
This
that's
is
just
for
the
uniform.
yeah.
This is in the case where all of the B successor states are uniformly likely. But what this is showing here is that after after like 20% of the computations that would be required to do the expected update, the error for this large branching factor is already been reduced to just 2%, right? And here, this thing with the expected update is showing like the expected update cannot produce an update until it has computed all of the branches. but, you know, it's like, I
Oh,
mean, 20% of, like, this is still a large number of samples, right? This is like 2,000 samples, but, you know, it's not nearly 10,000, but, you know, we've already covered a lot, you know, a lot of the probability. But yeah, in this case, you know, all of the branches are uniform. So in this, you know, like if you imagine we're just averaging up all these together, so they are all right. These would all have equal probability. Whereas, I mean, you could imagine an extreme case where, let's say, one of the successor states has a 90% probability, and then all the rest are the remaining 10%. Right? So for this update, we would take that 90% one, we would weight this term by that 0.9, and then we'd have to add up all the others as well, weighted by the small probability. Whereas in the sampling case, we would just be sampling the transitions and, you know, however many we do, like 10, 100, and we would just consider the reward and the S prime from whatever we actually sampled. But in the case where it's uniform, then these S primes that we transition into would be sort of appear with equal probability when we take the samples. So, but you know, we wouldn't be able to cover all of them in, you know, less than B samples. You know, however, for each sample, we are getting this R value, right? So, right, the value is a combination of the R and the bootstrap value. So we don't get that many, like, we don't cover that many of the successor states in this small number of samples, but we're getting some of them. But for each one of those samples, we are accumulating in one of the rewards, which, you know, could be in some problems a substantial component. Actually, in this, for this plot, I don't know if they're actually considering the R. The whole value may just be from the successor state. I mean, it probably is in this case, and it still has this, you know, this positive result with small number of samples.
May I ask a quick question?
Yeah, sure.
So I'm new to this chapter and rest of the book. I'm joining first time for the meeting. Here it says unexpected updates. What does it mean? With particularly in the middle, 1B.
So the expected update would be given by like this equation. It's called expected because you're computing an expected value with the probabilities.
Okay.
So if there's B successor states, like S prime here, where S prime are the successor states, then this computation would involve B terms in it,
Okay.
and also B evaluations of this max A prime. So like this is the thing that we're saying is like, how many of these do we have to do? So for the expected update, we have to do B of them.
Okay.
For these updates, each one is just a single one, so we can do as many as we want, up to B or as few as one update. Right? So this is showing the error. So in this example, once we complete one expected update, we've reduced the error to 0. So this gray line, or here on this plot, it might be easier to see, is just showing that if we have the time to perform an expected update, which would be B computations, then we'll just do it and get the error to 0. But like this would show the case where, let's say we can only do
less than B.
B over 2. You know, so the expected update has no error value for B over 2 because it's not done yet. So we would be just the same as if we hadn't done anything. So that's why like the expected update only makes sense after B updates. I mean, it only makes sense at B updates because, you know, if we can do this many updates, the claim is just you should just do the expected update.
Okay.
It will eliminate the sampling error. But, you know, it depends on the problem. So B here specifically refers to, for a given state action pair, how many successor states do you have to worry about? Not so much, this actually doesn't matter. The reward, there could be different rewards, but those can be computed separately, can be averaged out. The problem here is really the S prime states. Like for a stochastic environment. So in the case, if we look back at like, you know, like in the maze environment, this is deterministic. So the branching factor is 1 because for a given state action pair, there's only one successor state. So the branching here doesn't matter actually how many like state action pairs there are. Like here, there's 4 actions. So the paths can branch with a factor of 4, but the environment isn't stochastic with branching. So these examples so far, none of them are actually stochastic environments. But this is sort of imagining you have one.
Okay.
I mean, but this would be an environment where for a given state action pair, you could end up in one of 10,000 states, which would be, you know, I mean, that's a lot of branching.
Okay, got it.
But yeah, this would make more sense. And like, I mean, there's a lot of situations where this could make sense, but you know, like in a game, like in chess or something where the next state you consider is after your opponent's move. So you are in a state, you make a move, and then the state you end up in, like if your opponent is playing randomly, then if they have like 100 moves that they could make from there, then this branching factor would be like 100 because you could end up in any one of those 100 subsequent states. But, you know, that's like considering the game after your opponent's move. If you consider the game after each player's move, then actually it's no longer a stochastic environment because, right, like after a move is made, you actually know exactly what the board looks like. So that's a different, but you know, that's not the way we would formulate the problem here because, you know, your opponent is not the same as you. So you have to do something differently where you treat them. You have to change something about the environment, like between each opponent. But there is another example of a stochastic environment later, which we could look at. Yeah, but anyway, but going back to this, so but you know, if you think about this exercise where, you know, so this is showing how the sample updates are more efficient if there's high branching, even if the branching is uniform. But what if the branching is not uniform? Like, what if it's really skewed? So even though there's like 10,000 successor states, only 5 of them are actually very likely. Then how would that change this picture? So I don't know if anyone wants to think about that more. Hopefully it shouldn't, I mean, it shouldn't be that difficult of a question based on what we've already talked about. And, you know, these equations.
Yeah, but we will, even if it is skewed, we will be able to find out through little bit of exploration, right? And the learning constant, applying that.
But,
I
you
mean,
know,
I read the
that's
book a little longer ago, so just.
Oh yeah, well, I mean, here, like this is sort of a simplified example. We're not really talking about the stuff with Dynaque and exploration. Here we're just sort of considering performing an update on this state action pair,
Mhm.
where we're just either sampling, you know, from the environment.
Well,
And remember, there's no policy here, right? Like we've already picked the action. Okay.
well, since of the previous result of when having a uniform probability of different states, that it doesn't affect the sampling one, because it would still be dependent on one be a branching factor. But for the expected update, if that probability is skewed, then wouldn't it converge more quickly in the case with less branching necessary if the distribution of states that would be of interest.
Mm-hmm. Yeah,
interest
so if it's skewed, then this sum, like certain terms are going to be much more important than other terms, but we still have to compute all of them. In the sampling case, though, you'll end up sampling more frequently the skewed successor states, right? But those are also more important in this sum. So it should actually converge even faster than it's shown here if it's skewed. And most environments will be quite skewed. So the point is that as good as sample updates look in this diagram, they actually are probably even better than this, like practically, because we often have skewed
Well, I guess it would make
probabilities.
sense, given that if you have any robotic system, and if you try to map out the state space of it based on the different angles and velocity at discrete intervals, then a lot of the states of that robotic system would be completely useless if it's a walk-in robot, where a lot of those states where the legs are just rotated not on the ground but on the ceiling itself, just kind of useless.
Oh yeah, well I think you're talking more about the branching in the total state space. Here we're really just talking about branching from a single state action pair, right? Because there could be a lot of actions here, but we're only really talking about one of them. And a lot of these environments we talked about are not, even though they have a lot of actions, they're not actually stochastic. But yeah, this is like more relevant in a case of like the game example or in a robot example where there's something the environment could do to the robot in between the next step. So then, the state you end up in is based on something in the environment that you can't control. But hopefully the robot, when you tell it to move in a certain way, it actually moves in that way reliably, and there's not like one of 10,000 things that the robot could actually do when you try to tell it to do one thing. But yeah, there's different ways of setting up, of like discretizing the problem. But okay, we can move on to this trajectory sampling section. So this actually also could relate to the dynamic programming stuff we already did, where if you recall, like when we did dynamic programming, we might like perform an update like this, and we would have to do it in general for all the state action pairs. Like we have to keep doing this until it converges. And with dynamic programming, we just swept through all the state action pairs in order, and that was it. And in trajectory sampling, there's a different proposal, kind of like the prioritized sweeping thing, where at any given moment, like we have the current Q function that we're estimating, and it hasn't converged yet, but you can compute an optimal policy or an epsilon greedy policy from that. And then you could imagine taking steps in the environment with that, and those steps would correspond, to the on policy distribution of state action pairs for that policy. And the idea in this trajectory sampling is that updating those states is more important than just sweeping through all of the states. So in trajectory sampling, which I guess it doesn't really actually show pseudocode for it, but here, go down to here. So how did I sort of adapted this from the previous dynamic programming code, but here I have, so for the uniform Bellman optimal value update, you just iterate through all the state action pairs and you perform this Bellman update, in this case for the Q function, not for the, right, we're sort of what we're doing this update for all the state action pairs. In the trajectory sampling, what we're doing is we're taking the Q function, we're computing an epsilon greedy policy from it, whatever it is so far. Then we're gonna take steps from the environment, but in this case, the step isn't actually to do a sample update. The step is to get the successor state that we then use for the next Bellman update. Right, so like these, you know, like whatever state action pair we're in. So that's the only difference between this, is here we're just iterating through all the state action pairs. Here we're using the environment to step the Q function we already have, and then, you know, we can repeat this for multiple trajectories. Like this is a case for an episodic task where there's some terminal state, but you could also do this for a continuing task, and you would just have some other termination condition on this. So, you know, this is fine as long as we visit all the state action pairs with some probability, which is why we do the epsilon greedy trajectory, because that will make sure we visit. Now, obviously, if you iterate through all the state action pairs, that's one way of guaranteeing you see all of them. But in this case, we are focusing the updates on ones. And the idea is that, you know, a lot of the states that aren't along the optimal trajectory aren't that important, or they don't need as much computation devoted to them to do the update. So this is one way of doing this. And there's this example here. So in this example, they generate some sort of synthetic MDPs. And in this, I mean, they're sort of combining a few different concepts here. I think like the way they compute this is actually with this value iteration step for some number of steps, either sweeping through all the states or doing this trajectory sampling. But in this case, you're sort of imagining that this this value iteration update is sort of akin to the planning phase. Like if we had a model, instead of like explicitly building a model from the MDP, we are going to generate an MDP by having some set number of states, and then we're just going to have some branching factor on the MDP, where from every state, for every action we take, there is some sample of those states, B of them, are reachable with uniform probability. So it's the same setup we had sort of before with this diagram. Like this B means the same thing. So it's like the number of states reachable from a state action pair. And then we're gonna perform these updates, you know, assuming like if this environment represents some model of data we have, it's very stochastic. The rewards are stochastic. For every state action pair, there's going to be some expected reward, which is random. But the point is that, like, you know, whatever the model is, or whatever, you know, the MDP is, we can see what, you know, as this value like converges, it should get higher and higher as it converges to what is actually the optimal policy and the optimal value function. And of course, as the branching is higher, the environment's more stochastic, it takes longer to converge. And what this is showing is if we do the on policy version, where we're sampling using the epsilon greedy policy, the trajectory sampling, or we do the uniform sampling like we had before, where we do this. And so this is showing how, with very low branching factors, the on policy trajectory sampling seems to converge much faster. And, obviously if we wait long enough, if we have infinite time, we should do uniform sampling because that meets all the guarantees. But just like the prioritized sweeping stuff, this is more asking like, what if we just have limited time? What approach should we follow? And there is some point where the branching gets large enough that the uniform sampling, just more quickly overtakes the on policy one. So you can see like the higher the branching factor, this crossover point is moving further and further back. And at some point, like they don't show it here, but if the branching is large enough, you probably, never really have much of an advantage to this, trajectory sampling. And you're better off just checking everything. But so here I have this example here. So this is sort of showing about the same thing. So like this line would be showing the value with the on policy sampling, and this would show the uniform sampling. And then we have these crossover points here, branching. This plot is showing the same thing, but with a much larger state space. So here, like the state space is very large, but the branching is not large. And you can see this seems to be the best case scenario for the trajectory sampling, where we basically, in this case, we have a deterministic environment. So in a deterministic environment, the trajectory is like very, very valuable. Like it's a very good indicator of what states we should actually care about. Now, in this exercise here, they say replicate this larger one with a branching factor of 3. That is shown here. So here we have the orange line here is the uniform, which I can get rid of this. So the orange line here is the uniform sampling, and the purple line is the on policy one, or the trajectory sampling. So we have sort of the same, right, crossover phenomenon where, at some point, if we're willing to tolerate a large number of updates, it is better to do the uniform sampling. But I mean, at least compared to the fewer number of states, that crossover point seems to have moved out quite a bit. Right here, it crosses over after just like 6,000 updates. But here, it doesn't cross over until over, 100, and 40,000 or something updates. So it seems like the larger the problem, the larger the state space, like relative to the branching factor, the on policy trajectory sampling, the efficiency of it is more pronounced. I'd say I was just I was trying to get this to work shortly before this, so I haven't had that much time to think about this. So I don't know if anyone else has any thought or idea after reading this, but the story seems to be that the larger the problem, the larger the states, the more benefit you get from trajectory sampling. Does that make sense to people? Or seem like what you would expect to happen? there's also this exercise. It says early, so they're talking about for some of these cases in the uniform sampling, early portions of the graph seem to have this dip in them. And what is the cause of that? Why do you think this is? What aspects of data support your hypothesis? I mean, it seems to get, so that effect doesn't seem to appear. Oh no, sorry. It does appear in the case of a deterministic environment. So why is there this sudden increase? I mean, I would guess again that this effect may be from how far away the initialization is from the true value. Because here everything was initialized at 0. And then after a single sweep through the state action space, there's this huge improvement. And then the improvement is less for the next update. Yeah, I'm not actually sure why this is happening. I probably have to think about it more. Unless someone else has any, any thought about this, particularly for B
No, I
one.
don't know. Not that we are sleeping.
Yeah, I mean, I guess they point out B equals 1. So for a deterministic environment, so why would a deterministic environment have this? In a deterministic environment, remember all these updates, there's only one thing to sum. It's just this, and all the bootstrap values are 0. I mean, I would say maybe it's because when you start out, all you're doing is accumulating the reward values, and you're not affected at all by this. And then the next step, you're using the bootstrap values, which are not converged yet. So there's some maybe temporary like effect on how quickly it converges from these incomplete bootstrap values. I don't know why it'd be worse for, and there's only like a single successor state that you're considering too. Whereas the higher the branching factor, then this sum is occurring over more of these. So maybe more of the effect is like washed out when you can sum over more successor states versus just a single successor state. But I'm not sure exactly what they're getting at here. Also in my plot, because I don't have, well, I didn't start at 0, but you don't even really see the same effect the way I did it. So I'm not sure exactly. Okay, we can, I think for the remainder of this chapter, they just sort of bring up other things. I don't think there's any more exercises at all. Not right. So I don't think we don't necessarily have to talk about all of it. I mean, I would actually like to do this with the racetrack problem. I haven't done it yet, but in this case, it's like kind of like the trajectory sampling, I think. But in the trajectory sampling, you're sort of imagining it's part of the planning process. But in this case, we're doing the dynamic programming like we did before with like sweeps through the state space, but using trajectory sampling. And I think in this case, like actually doing real trajectories through the environment rather than using like any kind of model that we have saved. I think that's what they describe here. And there's also a point here about there may be some states that are not even reachable, or some state action pairs that aren't even reachable from the under the optimal policy. So in that case, we don't actually have to consider them in the update at all. So as we continue to do these sweeps to get the convergence, once we've arrived at the point where we know that certain state action pairs are not going to be visited, we can just ignore them. And they have, I mean, there's no plot here or anything, but they claim that this is how long it took to converge using dynamic programming. Whereas in this case, they only had to do 4,000 episodes and quite a bit fewer actual updates to have convergence. But I think the episodes must be following, I imagine they're following the epsilon greedy policy according to the Q function. But yeah, I mean, but this is not nearly as dramatic as an improvement as we had before with the prioritized sweeping or, you know, the trajectory sampling here, where it was like, you know, we already like mostly converged after, you know, orders of magnitude fewer updates. I mean, this is still taking quite a long time, but there's probably other problems where this would work. But yeah, this is again just a case of, you know, choosing which state action pairs to update based on where we're likely to get a meaningful update. So all these methods have sort of have the same similar idea of trying to do more meaningful updates. So this is just another example of that. The final part of this chapter is talking about a different type of planning, where in the past we used planning as a tool to converge the value function, and we were trying to learn the optimal policy across the whole environment. This section is talking about planning when we actually are deploying a policy. So like the policy itself would be able to do planning in real time when it's making a decision, as opposed to using the planning to learn something ahead of time. So I think probably the best way to talk about this is sort of with in the case of the rollout algorithm, and there's sort of a nice connection here to the policy improvement theorem from before. But so the idea is like, you know, let's say like we have learned some policy, like from any one of the techniques before. So, you know, we have a policy which is good, maybe it's not optimal, and can we do anything to improve it, you know, at the time of actually using it? And with a rollout algorithm, what you do is, like, let's say you're in a state, like some state, then the policy itself would tell you like to take a particular action. But for now, like, let's forget about what the policy tells us, and let's just look at all the available actions that we have, and let's take them in some, well, actually here we need, in order to do this, we do need a model. So this will only work in the case where we have a model of the environment that, you know, may not, like a stochastic model of the environment that may not match like the true environment that we have. But, you know, there could be some hidden information. But let's say we have access to something that can allow us to simulate trajectories from the policy. So we can look at each state action pair, and then we can use this model or this simulator to arrive in a new state. And then from that new state, we can use the policy we already have. And we can sample, we can take a lot of trajectories, and we can look at the results, and we can average them. And that average will be an estimate of the value of these successor states under the policy that we currently have. Now, this logic is what we used before to come up with the, SARSA and dynamic programming and like all of the techniques that compute an optimal policy. But if we have the value function for the current policy, or in this case, if we have the value estimates of all the actions we could take under the current policy, then if we choose the action that is maximal instead of the action the policy would tell us, then that is a strictly better policy. And this is what we had before from the policy improvement theorem. So in the case of using these rollout algorithms, you just sort of do that once for the state you're actually in. Because usually, like when you're deploying policy, you only care about the state you're currently in. Like you don't necessarily need to solve the whole environment. So it's like we have a policy, we have a simulator, we can compute the value estimates for all the state action pairs under the policy. And then, maybe it will match the policy, in which case we'll just do the same thing. But if we find something which is better, then we should do it. And then we are strictly following a better policy, like one step of policy improvement in that case, which for some problems could be significant. Like if you go back to some of the grid world examples, even from a random policy, once we computed the value function for the random policy, the greedy policy with respect to that was already the optimal policy. So for problems where like you can actually reach the optimum from one step of policy improvement, this sort of rollout approach is very useful. And an extension of the rollout approach is this Monte Carlo tree search technique, which is a little more involved than the single step rollout, because you end up building up this tree. And I don't actually know if it's worth going into now because it's a whole distinct topic and they don't provide pseudocode. I mean, there's like sort of an outline of how the technique works. There's not a lot of discussion of like theoretically why it works or what the guarantees are. But the idea is that, we're going to sort of build up state action value estimates for this. But in the rollout algorithm, we would just, try to estimate each of these successor states, the value using a rollout, and then pick one. In the tree search, you extend this down where you keep building the tree and you hopefully over time build up better value estimates for each of these. But there's, yeah, Evelyn?
So I apologize. I really do want to spend more time on Monte Carlo tree search, but I have to go. I think it's a good stopping place if you don't mind.
Yeah, well, I don't know if we can stop. Like next time this is sort of the end of part one. I mean, I don't know if we want to spend an entire time like wrapping up part one and talking about this because it's sort of a side topic. The alternative is just to move on to part two, but I mean, we could also do
that would be fine as well. But I just am not up to listening to Monte Carlo tree search at this time.
Yeah. So I mean, we could do like I don't actually know what we should do in the next meeting because starting part two is like a whole other thing. This stuff at the end of part one is not really new topics with that much information. I mean, although like there is this whole like summary section where we go over stuff.
That might be very helpful for people catching up who are joining partway through.
Yeah, I mean, I guess like we could just do a whole overview of stuff with the most interesting examples. It's possible. I mean, or if people have other like specific examples or environments they want to go over. I mean, one like natural thing to do at the end of part one would be to like pick a problem that maybe isn't in the book or something that seems like you're interested in solving and see which of the techniques would actually work for it and sort of actually like go through an example. So,
that would be really good.
Before next time, if anyone like has specific problems that they think would be interesting or that they've been like thinking about, wanting to use some of these techniques. Again, like these are like tabular techniques. The Monte Carlo tree search actually is a little different because you don't need like the problem. This actually works on problems that are too large to handle with tabular methods. So this is like the only example so far in part one that this can accommodate very large problems in theory. But the other techniques would require a situation where you can list out all the state action pairs, and that is not too large. But I did already have something in mind. I mean, I did apply this to the maze example, which is just sort of to test it. This isn't an interesting example to use it, but I do have this Wordle example I was trying to get working, which I have some success with, of using Monte Carlo tree search with this. And this, Wordle actually has a very high branching factor, because for any given, guess that you make, there's a lot of different possible feedbacks that you can get. So, this actually meets the criteria of some of the difficult high branching problems in the book. But this is also a problem where you can't enumerate all the state action pairs. Like if you consider states to be like games, like guesses and the corresponding feedback, that's already like too many states to actually write down. Because there's like, 15,000 guesses you could make per turn. And then for each one of those, there's like 243 distinct feedback values that you can get. So actually for a single step game, it's not that bad, I guess. It's only like 3.6 million states. Yeah. So, but then, a game can go on for 6 steps, so you have to multiply that. Well, actually, you have to take that to the 6th power, right? I mean, a lot of those might not be accessible. And then that's just the states. Like, that's not even the state action pairs, because, or no, sorry, that is, yeah, well, I mean, it's very high branching, and you can't really enumerate all of the state action pairs in the game. It's just too large. Also, you could also consider the state space to be the number of possible answers that are left out of like the total guesses. So like even if you restrict it to like you only think there's like 3,000 things that could be an answer, and you make that like a binary vector. So there's like 2 to the 3,000 states in that case, which is also too large to write down. So yeah, Wordle is definitely a problem that would need either an approximation technique or using MCTS. So we could talk about it for that. But yeah, if anyone has a different example or some problem or even like a real problem they have to deal with personally or some business thing they know about, it could be interesting to talk about next time. But yeah, I'm trying to think of ways of making something more interesting about doing like a summary of part one. And I think
I like the summary of part one, and I'm new, so I don't know if I would have something to bring up, but that will be also engaging to see if some other folks have some problems they are dealing with, they have to solve using RL at their work, or
yeah,
have some
well,
guess.
people can. Oh yeah, so this meeting has been recorded, and not all of the previous meetings are recorded, but if you're in terms of reviewing stuff,
Uh-huh.
you can like review the notes, right? Like that is all available on GitHub.
Okay.
And that, hopefully the notes are written in such a way that you can read it and,
Okay.
along with
And
the
is
book.
this the first meeting which is recorded, or there are
No, there's
some?
been others. If you look in the Slack, I posted them. I mean, some of them are posted
Right.
in previous meeting descriptions on
Okay.
Meetup, like in the comments for the meeting. I don't know, like a good place to post all the recordings. I mean, so far, I think just putting them in Slack is probably the easiest because that channel doesn't have that many messages. You can, if you use Slack, you can be invited. Someone could share the invite link, or I can try to share the invite link. You just have to open it up. But I take it you're not in the Slack. You're asking this.
So how will I search in the Slack? Um,
First of all, let me here copy. So here's the Slack link. And if you go to the reinforcement learning channel, you can just see the previous messages of, oh, I guess some of them are
okay.
actually expired. Okay, well, maybe I can make a new message that has all of them listed. I'm not sure. Is there any other place people would prefer me posting this? We don't really have like the Slack is the closest thing to any kind of place where we post messages. Or there's like the meetup, comments, but people don't usually look at comments from past meetings. So
Mm-hmm.
I don't know if that's the best way to do it. Or I just keep copying it in every meeting description.
Let me go over some and see.
Yeah, okay, but that works. So you can see the links to the previous recordings. Some of them anyway.
Mm-hmm.
Okay, well, yeah, I mean, people like, how to, like, anyone can message me either on Meetup or on
Yeah.
GitHub, and I think I don't know what other contact info I put in other material, but there's other links and things in the meeting description. But
Okay.
should be able to, yeah. So if you have anything you want to go over or look at, or specific examples that you think would be interesting for finishing part 1, you can send me a message. But I have some examples already, like this Wordle example, and there's maybe some other things I could think about to